Okay, thank you. This is introduction of Vijay Bhosle. I'm Sachin Umbarkar. On behalf of Vijay, I'm presenting this paper. So, title of my paper is calibration of transient field sensor using half TM antenna radiator sensor. In this presentation, Vijay did a lot of work on the sensor design. He developed a TM sensor and calibrated by using compare with the GTM and all other sensors. So these sensors are giving a experimental and a simulation point of view. Also, he did a lot of work on mathematics, and that sensor is I'm going to present over here. Now, presentation flow is like this: introduction, and then EWB system, that's applications and characterizations, work objective, and now the experimental results also will discuss over there, what are the sensors we develop, and conclusion on this slide. Now, initially that EWB is a subset of SPM signals. So this is the HPM environment, or there the EWB is a subset of this HPM. In this system, the measuring of picosecond pulses is a very, very critical and important task. So that purpose, we have so many sensors available, like so Prodynes, also we already buy it from the Prodyne companies, and DDOT and BDOT sensors are there. Or Vijay's laboratory in LRD and DRD also, they develop that sensor, and that sensors giving results in that way is comparable with the accuracy and its sensitivity. Now basically our system is having a pulse power source. There is so many sources, capacity base also. And this pulse power source is fed by 30 kV DC source, and if it is operated by the mass generator, then after that switch is there. This switch is playing a very, very important role because this picking switch is there. When we are feeding direct pulse to the switch, that time rise time is in nanosecond. Now by using a picking switch with a gas pressure arrangement, we reduce that rise time to the sub-nanosecond, that is picosecond. And then that picosecond pulse is fed to the antenna load. So in our APPD BRC laboratory, in VJTIs and LRD laboratories, we develop a similar kind of work which is developed by Curly Baum, that HIR antenna, then half TM horn antenna, and the different types of antennas so we develop. And we compare different types of results by using different types of load, which is terminating load to the antenna. Now, this switching modeling we did by using PIC code algorithms, that how the exact breakdowns happen at the higher pressure level. We played with this picking switch up to the 14 kg per centimeter square gas pressure SF6. Also, we tried for the hydrogen, and next time we are planning to test this switch for the 80 atmospheric pressure. Now, what are the pulses radiated by this antenna? That radiated pulse is measured by using a field sensor connected with balun, that is converting balance to unbalance, and then oscilloscope arrangement. So this entire system, this is a basic block diagram of our system, and this we are concentrating today on the what is the calibration mechanism behind this sensor. So these are some applications of UWB, that is secondary directed energy weapons. We also developed similar kind of setup like a Jolt system developed by Carly Baum in 2010, and that David. So this system, this Vijay laboratory is having LRD laboratory in DRDO, Bangalore. So this system measurement is important. Now, objective of this today's work is development and characterization of prototype 50 kV HIR-based UWB system using field sensor. And application available in situ methods are calibrated of sensors. The experimental validations of the best calibrated method for the various sensor types. So we compare with the different types of sensor and whatever the sensor developed in the laboratory. Okay, this is a setup available, is developed, and this is a small kind of setup for this is a source which is filled with a gas pressure inside SF6 we are initially tried. And then this at the top of this gas source, the switch is located, and the switch is fed by the gas line, and we are operating this gas by SF6 gas, and then feed it to the TM horn feeder, and this is the reflector type, so which is complete similar kind of work that half impulse radiating antenna, and this antenna is terminated by resistive load. So this is a preliminary work developed by Vijay and his LRD laboratory. This terminating resistor are in most of the non-inductive type, because we are launching some pulses on the reflector. That time it should not have some ringing effect. So we connect this sensor and we take care of this resistive termination load. So in this system, we have output peak voltage of 50 kV. Rise time is 300 picosecond and fall time is 1 nanosecond plus 125. Plus this antenna is a half impulse radiating type of antenna, and feed transmission line is 100 ohm effective lines, impedance of this feeding line. Now in this system, we tried this gas switch is inside this point. This is a source, then switch is located over here, and this switch is operated at different gas medium. That's dry air, nitrogen, SF6, and also we are trying for hydrogen. Now, this is a test setup for the characterization of developed UWB system for requirement of ideal calibration of setup. So this, whatever the pulse is radiated, is measured by using a D-dot sensor, and then D-dot sensor is connected to the balun, and then oscilloscope arrangement. So this is the exact setup test available, and we did the calibration setup as per the IEEE standard of this to employ the GTEM cell. Now, whatever the calibration sensor we developed is compared with the GTEM cell based method and AWG based method. So whatever the results, source use is the FIT GmbH 10 kV, 100 picosecond rise time, 1 nanosecond duration of the pulse. So this 1 nanosecond rise time of pulse is measured by using a sensor. In this both methods, this GTEM cell based method and AWG based method, we calibrate the output pulse. We measure the output pulse by taking care of the cable shielding and everything, so that should not introduce the extra additional EM field in that. So it is AWG based method is the output, AWG output is 50 picosecond rise time and 10 volt amplitude. And following issue we face during experiment, that when extremely low field coupling to the sensor due to the low sensor sensitivity, that time we are not able to calibrate the sensor properly. Also the connection compatibility issue between the AWG and GTEM cell. Hence both methods were not found to be suitable. So now finally, we finalized the last method, that using a half TM antenna radiator base. So this is a similar kind of the TM horn antenna, but the one plate is a ground and another plate is tapered one, with having an effective height, and this effective height is this, and whatever the source is there, that is radiated by using a half TM antenna, and these are the D-dot sensors and balun and oscilloscope. So this is the experimental setup, and we finalized this method to measure the radiated pulse. Now the sensor type with the sensitivity for different D-dot sensor and B-dot sensors are there. The percentage calibration error for the rise time measurement is 2.85, and for B-dot it is 3.62. So these are the B-dot sensors under the calibration test. Now, on this work, would like to conclude that the characterization of the radiated field, an important aspect of the UWB system. Sensor calibration is vital for the same, because we can generate or develop the any HVM source at a very, very low intensity, very high intensity also. But the calibration is a very, very important part, and that calibration should be done by using a very, very good sensor. So also we use the oscilloscope, which having the very, very high sampling rate. Tektronix oscilloscope we buy, it's a very high sensitivity, just a DPO series. And that's everything, the calibration, because doing experiment at a picosecond rise time is a very extremely challenging part. And if the environment, which is, if not anoic, it is in free space or somewhere, it's sometime bouncing pulses will come, and that will pick by the sensor. So that calibration is an important part. So that's why the sensor needed to be designed properly. Calibration, the various calibrations methods tried sensor calibration to characterize up to 50 kV UWB HIRA based system developed. The method using the calibrated STM antenna and the calibrated pulse source found to be best for in situ applications. The calibration error was found as less than 4%, and various BD dot and B dot sensors are developed. Thank you.
So questions?
Yes.
There's my microphone right behind you. Back. Way back. Corner. No microphone?
Yeah, we're waiting for the microphone.
I can also speak out.
Yeah, yes.
Can you go back to the slide where you showed your measurement setup, please? Okay, so there are rather long cables between your sensor and your balancing unit.
Yeah.
And I would assume that if these... There it is. So you have rather long cables between your sensor and the balancing unit, and I would assume if these cables don't have exactly the same electrical lengths, that would lead to a time shift of the signal along both lines and some phase shift in frequency domain. And I think this would somehow distort your output at the end of the balun. So how do you make sure that the cables have the same electrical lengths? Or on the other hand, why have you chosen this cable so long? Why haven't you used shorter cables between the balun and the sensor?
Yeah, it's a very good question. That because if we don't have the cable length properly, then it's an error in that, and we'll not get the complete proper synchronization of the pulse. So that purpose, we use a time domain calibration of a sensor. I am not exact sure about that, what kind of work Vijay had reported, but they calibrate the length of the cable by using a time domain analysis, and they found that it's, if you are operating or playing with the picosecond, measuring a picosecond pulse, that time the length of the cable is assured by time calculation. So I'm not sure, sir, exactly what way he did, but I'm trying to. If you need more details, so contact this person. I'm just presenting on behalf of Vijay. Yes. Thank you, sir.
I have a question regarding your measurement setup. How did you determine the field that's expected at the point where you locate your D-dot sensor? Was it done numerically, or did you some other calculations?
Sir, initially entire work we did by using numerically, and that's we did exactly center by using a CST development.
Was it a full wave simulation? Otherwise, you might have, you might know that this kind of antenna has a so-called transient near field, so that the wave shape changes in the near field. So you need to make sure that you're a certain distance away from your antenna until the usual radiating models can apply it. So you need to have that in mind. And it looks like, for me, you're a little bit too close to the antenna, and the other part is the effect of the ground plane, that you have radiation and reflection from the end of the final ground plane that disturbs your signal too.
Well, sir, this location we decide based on the near field zone and far field zone. So that calculation is dependent on the rise time of the pulse. So if you need a far field zone, so that length should be greater than d square by 2 RCT. So where the TR is the rise time of the pulse. From that, after that, it is a far field zone is started. So
it's not just the distance and the attenuation. In fact, if you're close enough to the antenna, if you go from the antenna a little bit far away, the signal becomes, the rise time becomes shorter. Dave Geary published a lot about that, and I did it, and Everett Farr. So you need to have that in mind, that this antenna is a little bit tricky if you measure too close to the antenna.
Right. So at that time also, at near field measurement is challenging for us. Yes. Yes, sir.
I think, this is Carlos from Montana. I think it's very interesting, your paper. I think we should be really careful on speaking about calibration. When this kind of calibration of sensors, we do produce this kind of sensors, and the calibration system must have an uncertainty that is less than the uncertainty than the system that you're measured. You should, in this case, for example, assure that the pulsar, all this system, cabling, attenuation, balloon introduced uncertainties, and all don't add up to the amounts that you cannot, that make the measurement you couldn't do it. In fact, there are some efforts, ongoing efforts. I can cite, for example, from Dr. Fa for calibrating, trying to do in the direction of calibrating this kind of sensors. But I think that we should really be careful when using the word calibration for these sensors that are calibrated by the rule as they are mechanical built. Yeah, thanks.
Yeah.
A comment on that. With regard to calibration, we should be very carefully showing this kind of numbers. As I know that the National Meteorological Institutes have problems to reproduce the volt per meter with 5%. There more tend to be more than. And so the uncertainty you get from your National Meteorological Institute is less than the number you showed here, and no one can calibrate a sensor better than our National Meteorological Institute. So you need to be sure what you're talking about.
Any more questions? So we should thank the speaker.
Yes, thank you, on and all, and thank you, Dr. Richard and Dr. Edescu. Thank you, sir.